Hello, and welcome to our video on adding nucleophiles to aromatics part 2. If you haven't already, you may want to check out part 1 in the previous videos. But assuming you've already seen that, let's go ahead and keep moving forward. As we introduced in the previous video, there's 3 different types of reactions where nucleophiles will add to the benzene instead of benzene being the nucleophile. Those are the SNAr reaction, the SNAr or the nucleophilic aromatic substitution reaction, and benzyne reactions. We've already covered number 1, a pure SNAr reaction, and also showed in the last video how to make N2+. Now we're going to talk about the SNAr and the benzyne reactions. So as you may recall from the previous video, we reminded everyone that you cannot do an SN1 or an SN2 reaction on a benzene ring. However, there's something similar, and that's called the SNAr reactions. So they're like substitution of a nucleophile, but with an aromatic. So we'll show how the mechanism's different in a second, but the first thing we need to know about the SNAr reactions is that they do have a leaving group, so that would be like in this example chlorine, but you could also have bromine is very common. And then it's going to substitute where the chlorine or bromine is. So that part makes sense. It's going to look a lot like an SN2. However, the mechanism is going to be different. The other thing you have to know is that there's a special requirement for this reaction to work. You have to have an electron withdrawing group, and it has to be either ortho or para from the leaving group. The leaving group is usually a halogen, as we said. So in this case, if it's meta, that would not be a SNAr reaction. It would have to do something else if it was meta. But if it's ortho or para and we have electron withdrawing groups, then that would be a good option for the SNAr. Now, what are some electron withdrawing groups that we can use? Below, I've shown some examples of good electrophiles for this reaction. Remember, in this case, the aromatic is going to be the electrophile. So if you look here, we've got all of these have chlorine, but they could also have bromine, but they have some electron withdrawing groups. So we've got a nitro group, which is a strong electron withdrawer, and also a CF3 group. So that's electron withdrawing because of all the fluorine groups, they're very electronegative. The nitro group, as we recall, is electron withdrawing because it has a full positive on that nitrogen charge, so it's one of the best ones. There's other groups you can use. For example, a cyanide would work, a ketone would work, anything with the carbonyl right next to the benzene would work, but the ones that I'll focus on will probably be the NO2 and the CF3. All right, so those are examples of the electrophile. So then that begs the question, what are the nucleophiles we can use? Because again, like in SN2, there's more than one option for the nucleophile, so the reagent part over the arrow might look a little bit different. So there's several options that you can use, but I'm going to focus on these here. So if you notice, all of these are O- type of nucleophiles, so they all have a sodium whenever you write them over the reagent arrow, but they would be a negative charge, for example, in the mechanism. So anything with carbons on the oxygen basically will work, so you might see them in this format. If you look at the bottom, the NaOH is slightly different. That's because whenever the nucleophile adds, it makes a phenol, and the phenol, which is a benzene ring with an OH on it, is actually acidic. It has a pKa of about 10. So then that means sodium hydroxide would deprotonate it. So it's one of those where you do the regular mechanism, and then at the very end, it gets deprotonated, and then you have to reprotonate it. That's what the H3O+ is for. And that's actually going to happen anytime you make an OH on a benzene ring and it's in a basic solution. So now that we have an idea of what the reaction could look like, since there's several variables, let's look at a few more examples and the mechanism. So first, let's look at the mechanism. We'll look at the example on the top. So as we see, this is definitely going to be a SNAr mechanism because it's got an electron withdrawing group. And where is that electron withdrawing group compared to the leaving group? Is it ortho or para? It's ortho, right? Because it's right next to it. We also might notice that the nucleophile, while it's a base, is not a super strong base. So that is a distinction we'll want to make when we get to the next reaction. So that'll work. And so let's look and see what it looks like. All right, so the first thing we're going to do is draw the nucleophile. Remember, it has to have a negative charge for the mechanism part. So we'll redraw it here, and then we'll put an O- instead of the sodium. Then it's always going to attack where the leaving group already is. So it's going to be nucleophile attacks at the very first step. It's going to go from the negative charge to the carbon with the leaving group. Then instead of the leaving group coming off right away, because that would be SN2, the electrons are going to go up from the benzene ring. So they're going to go to the next carbon over. So just wherever that double bond is, have it go to the next carbon. In this case, it's going to end up being look like this. So then it's right next to the nitro group. So that explains why we need the nitro group, because it needs to help stabilize that negative charge. Now, if this was para, this would still work though, right? Because there can be resonance where the negative charge can alternate on this carbon or this carbon or this carbon. So as long as the nitro group's on one of those carbons, it'll still work. You don't have to show that resonance, but it's good to know that that's why that's there, okay? Okay, so we made this intermediate. If you notice two things about this intermediate. Number one, it's got a tetrahedral intermediate, right? The carbon here has the chlorine and the nucleophile that just added. That's a tetrahedral carbon because it has 4 things attached. Also, this is no longer aromatic, right? Because the negative charge can't go all the way around. So we need to restore the aromaticity, but the way we're going to do that is we're going to have the negative charge come back down and push off the leaving group instead of removing a hydrogen. There'd be no point in removing a hydrogen because it's already negative, so don't do that. So instead, electrons from the negative charge come back to where they were on the double bond, and then the chlorine's going to leave. And then that makes our product, so this mechanism is done. Now, what I think is interesting about this reaction and makes sense to do it now as opposed to earlier is because if you look at this mechanism, it should look like another thing we've seen before. So imagine that this is not a benzene ring, but it's something else where something attacks a carbon at a double bond, then electrons go up, then it makes a tetrahedral intermediate, then electrons come back down and make the leaving group leave. What mechanisms have we seen that do that? Right? It's like nucleophilic acyl substitution, where you have a carbonyl with a leaving group on it, like this, and then the nucleophile will come in, electrons go up to the O minus, then the electrons come back down, and then the best leaving group of the choices leaves. So for both of these, there's a tetrahedral intermediate, right, where there's carbons that are sp3. Also, for both of these, the electrons are going up for a reason, right? For the acyl substitution, it's going up to make an O minus. That's very stable. In this case, since it has to be on a carbon, that's why we need the electron withdrawing groups. So it works. So the last example for this reaction is another example where we've got an electron withdrawing group, right? In this case, it's a CF3, and it's got a chlorine para instead of ortho, and it's got sodium hydroxide as the nucleophile. So the first two steps of the mechanism would be the same, right? The OH minus would come in, electrons would go up, then we show them coming back down and the chlorine leaving. But then what's different about this one is we have to show the H3O plus. So we draw the product here, but then we would deprotonate it with the sodium hydroxide, and then we would add the H3O plus at the very end. So there's an extra 2 steps on the end, but the rest of the mechanism would be the same. So as I said before, anytime you're making the phenol, that's a special case because phenols are very acidic. So this last 2 steps will work for anything where you have a strong base, but you're making a phenol. So the next reaction will also do this for the phenol example. All right, so it's time for our final example of adding a nucleophile to an aromatic. For our first strategy in the SNAr, we had a really good leaving group. For the second one, for the SNAr, we used a special electron withdrawing group to make it better with just a medium nucleophile and an okay leaving group. So now our last strategy is going to use a super strong base as the nucleophile. And we're also going to see it's going to have a totally different mechanism where it's not going to look like an SN2 type thing. It's going to look different. All right? So for this example, for benzyne reactions, they're always going to have a very strong base as a nucleophile, or they're going to have to do something to make it act stronger. So that's the key. We're still going to have a halogen as the leaving group, so they look similar to the ones we saw before. But remember, for the SNAr, we had to have electron withdrawing groups on here. And for these, as you can see, they're just a plain benzene in this example. You can have other groups on there, but in this case, it's just a benzene. Okay? So then if you look, the 2 types of things we can have are we can have sodium amide, which is the first base. That's a pKa of about 37, so it's a very strong base. It'll work just by itself. And then ammonia works as a solvent and also as a source of protons. We're going to see we're going to need that. Then for the second reaction, we use sodium hydroxide. You could have a bromine or a chlorine for that one. They're not matched specifically. I was just showing the different leaving groups. But sodium hydroxide can work. It's just if you use sodium hydroxide, because it's a weaker base, you're going to have to use heat to basically make that nucleophile even better, to make that reaction more likely to go. Again, you need a proton source for this one, but in this case, it's going to come at the very end. All right, so let's get into the mechanism for these reactions. All right, so let's talk about the mechanism for a benzyne reaction. As I said before, this is a different mechanism than what we've seen before, so it's going to look maybe a little strange, but we'll explain later what the evidence for this mechanism is. But first, let's actually talk about what the mechanism is. So as we said before, we need a strong base, and that's because instead of doing it just as a nucleophile, we're first going to use it to do an elimination type reaction. So first we're going to have the redraw the nucleophile, which is going to be your base, with a negative charge. And the first thing it's going to do is do an E2 step. So that's elimination in the very first step. Remember, E2 is where you remove the hydrogen and the leaving group at the same time. So we're going to remove this hydrogen here, and it's going to come get that, and then that's going to go in to make an extra bond, and then we're going to have the bromine leave. So this intermediate that it makes looks like this. And that looks weird, right? Hopefully you think that looks weird. We've never before shown a triple bond inside a ring. So what they say is that based on the evidence that we've seen, it's probably not a normal triple bond. It wouldn't be a normal sp3 carbon because that would be a 180-degree angle and that won't work inside a ring of this size. So they think it's basically a diradical. So like they think it looks something like this over here, but you don't have to draw that. You can just draw it the way we've shown with the triple bond, but just know like that's not exactly how it behaves. It doesn't behave exactly like a normal triple bond, okay? So that's the benzyne intermediate. That's the key intermediate. Then once you have the benzyne, that's going to be very reactive, right? That's not stable. So what happens next is the NH2 is now going to be a nucleophile. We know we need to add it, right? So we're going to add it to this carbon here, and then that's going to push the electrons up. So now instead of being a diradical, we've just got a normal anion. So that would look like this. And then once we get the anion, we have to put a hydrogen back on there, right? So we're going to put a hydrogen on the side, and then that's going to replace it, and that's going to make it look like it just substituted, but really we took a hydrogen off and then put it back on. Okay, so that's the mechanism. It's not very long, it's just kind of weird. So now that we've seen those steps, let's talk about why we think this benzyne is actually a thing. Like, why do chemists think that's true? Let's look at the evidence. So the most obvious ways that chemists will use to try to explain a mechanism is a labeling experiment. So in a labeling experiment, they're taking either one of the carbons or hydrogens in this case, and they're marking it in a way that's using an isotope. So in this top example, I've made a little star where the carbon that's a carbon 13 is labeled. So you see at the top, we put it where the bromine is, right? That's where the bromine goes. And then what they found is the product is not always where the bromine is, right? If that was a SNAr, it would be the nucleophile adds exactly where the bromine leaving group is, right? But in this example, sometimes it was there and sometimes it was off to the side, right? All right, so that's one way. Another way we can do experiments is to label the hydrogen. So hydrogen, usually you would use deuterium, so that's D. It just means hydrogen with a mass of 2. That's where it came from. So we can put the hydrogen on there and see that if it gets removed or not. So if you look, there's a D in the starting material, but then there's not a D in the product. And that's because in some examples, that would be the hydrogen that got removed, right? So you remove the hydrogen on the bottom to make the benzyne, that would work. Or in some cases, it might not be the hydrogen that's removed because you can remove it from the top carbon, right? That's next to the nitrogen also. So there's a pretty equal chance of it being one hydrogen versus the other. So those would probably be a 50-50 ratio. Always going to be the hydrogen that gets put back on is going to be from the NH3. So that would definitely not be deuterium. So that's where the deuterium would go, is it gets removed and then doesn't get replaced. Or it stays on there and then doesn't get moved at all. All right, hopefully that makes sense. So those are 2 ways that we can know. There's other ways though, so let's look at a few more examples. So another classic way that chemists use to figure out what's going on in a mechanism is they'll add some things on the side, especially for aromatic groups. They can add electron donating and electron withdrawing effects. So what they find is there's different inductive effects based on what type of group you use. If you look at the top, we're using electron donating group. That's what that stands for. So if you use an electron donating group, that actually causes the nitrogen nucleophile to add close to the electron donating group and adds at the top where the bromine was. If you add an electron withdrawing group, instead the nitrogen's not going to add next to the electron withdrawing group, it's going to add further away. The reason for that is because whenever you get the anion part on the aromatic, you don't want it to be close to an electron donating group, so in that case it goes on the far side. But an electron withdrawing group would stabilize a negative charge, so it wants to be close to that electron withdrawing group. Now, in this case, we wouldn't have any sort of resonance for that intermediate because the negative charge is not part of the pi system. So remember, it can't move around in this case. So that explanation makes sense based on the mechanism proposed, whereas if it was a mechanism where it directly attached to bromine, there'd never be able to be a different option, right? That wouldn't make any sense. So that's another example. But there's one more left. So the last way that scientists have verified that there is such a thing as a benzyne intermediate is they just made it a different way. So another way that you can make it is you make a carboxylic acid next to a diazonium ion. So what we show on the left is basically the deprotonated version of the acid in that case, and then they heat it up. So when you heat it up, you can decarboxylate this reaction. So decarboxylate means remove CO2. So to do that, you draw the arrows like this, and then that will collapse to make an extra bond here. And then, as we said, N2 is a great leaving group, so that's going to really push this reaction to go forward. So then that's going to leave also as nitrogen gas. So you get CO2 gas, nitrogen gas, and this mysterious triple bond-like thing. then to prove that that's what they had, because it was hard to tell from the spectra data, they actually did a Diels-Alder reaction. So if I was to add something with the diene over here, then I would get this product. And they can definitely define that product, and that makes sense. It looks like it got added with a triple bond, but it's also with the benzene ring. So that's another way they do. So again, being a chemist is part being detective, because you can never see exactly what you're doing. You always have to think of experiments to come up with neat ways to figure out what's going on. So hopefully that was interesting. You may see some examples of cool stuff like this on the activity that I provided. But with that, we are done with our discussion of substitution on aromatics. Hopefully you found it enjoyable. That's the end of our videos for today. Make sure to check your course website to see if there's any activities and ways to practice, and let me know if you have any questions. I hope you have a wonderful day and that this video helped you in your studies.